All right, I think I'm live. Hello to anyone out there. This is basically going to be a sort of test run. Doing these sort of live streams is something that I'm sort of interested in doing to provide a resource so that people can learn R while getting their questions actually answered. I am still learning how to do this though, so we will see how this goes. This is going to be sort of like a dry run. And my first task is to see how to change the stream title. All right, here we go. First R stream. Let's see if this will actually update anything. All right. Cool. Well, thanks to anyone who is watching this for stopping by. If you're here, go ahead and say hi in the chat for me. Thanks for bearing with me while I got set up here. Okay. Great. All right, so before I get started here, I want to talk a little bit about my motivation for doing this for anyone who is checking this video out anytime in the future. Basically, my goal here is to try to create a resource that allows for more sort of back and forth and interaction between someone who has access to knowledge, which is myself, and someone who is maybe still learning R or maybe wants to pick up a few tips and tricks. I don't want this to be like other workshops that I've done where it's like one person gets up in front of the room and sort of gives everyone our knowledge, and then it sort of ends. My goal is to hopefully try to create some sort of community here, so that people sort of can come in and ask questions and develop a group of people who can go to each other for support if they're having some issue with an analysis or some code or something like that. I'm not going to be the only person who's streaming programming. There are sort of plenty of other people out there who are doing that. David Robinson is one person who does Tidy Tuesday every week and does a screencast, which is really cool. I want my content to be a little bit more tutorial focused, a little bit less just kind of playing around with data, just to sort of fill a different niche, so to speak. So that's basically my goal for this space, is for people to come by and maybe learn some new stuff and just have fun, meet some other people who are using R, and to try to build like a little bit of a community here. Because this is sort of a dry run, I'm learning how to do this and how to actually run a stream. I didn't want to start with a tutorial. I want to start with something just a little bit simpler and easier. So I'm just going to be playing around with this penguins data set that was the Tidy Tuesday data for this week. So like I said, I probably won't be doing these sorts of exploratory data analyses in the future. I think I'll do something a little bit more tutorial based or maybe even some longer term projects. But it seemed like a good place to start for my first stream. This data set is supposed to be a replacement for the iris data set, which is built into R. So with any sort of version of R that you have, you can type in iris. You don't have to load any data. This is just sort of available. And this is a really handy data set. You'll see in tutorials all over the place. The problem is the history behind it is a little bit problematic. The statistician who sort of first published this data, Robert Fisher, was known in part for opinions about race and intelligence and eugenics and things like that. And so if you actually look at the documentation for the iris data set, at one point there was a reference, so the source, Fisher, Annals of Eugenics. Okay, not ideal. So Alison Horst, I think I'm pronouncing that name correctly, has been sort of advertising this penguins data set that sort of will fill a similar niche. It has some continuous data. It's got some categorical data. It allows for some simple sort of classification type tasks, which we'll be playing around with here. And she's also created some really cute art to go along with it. So definitely check out the GitHub repo for this Palmer Penguins package. You can go ahead and download this, and then you'll have access to this data set as well. All right, so I'm just going to go ahead and get started here and just sort of explore this data set. I've never looked at it. I've just sort of seen like a few plots and things. I prefer to work in R Markdown. So let's just call this penguins. And I'll go ahead and create an empty document here. There we go. I'll go ahead and stick that on my desktop. Okay, cool. If you're wondering why my default R Markdown document looks different from yours, you can actually control what this blank R Markdown document looks like. Saves me a ton of time because I don't have to deal with setting my ggplot theme. I don't have to load tidyverse every single time I boot up R, which I do always without fail. So that's sort of a handy piece of tech already. Okay, so let's go ahead and get this package loaded here. And I'll just go ahead and print out the head so we can take a look at it. You'll see there's actually a penguins raw that comes in this package as well. I'm not really interested in that today. The penguins version is sort of all cleaned for us so that it's a little bit less work just to get our hands on it and play around with it a little bit. So, okay, what do we have here? Well, I know similar to the iris data set, there's sort of a few different species of penguins, and we have this sort of interesting information about them, their bill length and their bill depth, and then their flipper length and their body mass in grams. And then we have a categorical variable here, sex, and then this data was collected over multiple years, I think 2007 to 2010, if I remember correctly from sort of when I was poking around earlier. So we have a few different useful columns here. I want to build up to doing a classification of these different species of penguins. But to start, I'm just going to go ahead and plot some of these columns and see what we're working with here. I already see there's some missing data, so that's going to be good to pay attention to. I'll probably go ahead and decide to filter some of these columns out. Like this one is missing pretty much all of the useful information we would need. But first things first, let's just go ahead and take a look at these different values we're working with here. So I think there's 3 species of penguins. So I want to go ahead and just print those out and confirm that. Okay, so this is a factor. It's handy. I don't know how to pronounce these species of penguins. Adelie, Gentoo, and Chinstrap. Chinstrap's easy enough. Cool. Okay, so it is 3 like I thought. We'll go ahead and probably do some sort of classification, like a regression or something here to try to predict these later. Let's go ahead and do the same thing with the different islands and just see how many different islands there are. Okay, 3 as well, so that's handy. I don't know if the species is sort of completely limited to one individual island. Probably not, but I'm sort of curious about that. So I'm going to use count, and then I will count the species in the island just to get a sense of how many different species are on each island. Okay, and this is useful. So it looks like this one particular island only has this first species, and then these other 2 islands looks like the Dream Island has both Chinstrap and Adelie, however you pronounce that. And then the Bisco Island has Gentoo and Adelie as well. So, okay, good to know. It also looks like we have a bit of an imbalance here. So this species is the most common, and it looks like the Chinstrap species is a little bit less common than the other 2. So good to know. All right, so moving on here. I just sort of want to get a sense for the ranges for all of these values. Go ahead and plot some stuff here to take a look at. We'll just start with bill length in millimeters. It's really nice that they put the units in the actual column name so that you understand the data that you're actually working with. I really like that. Let's go ahead and just plot a histogram here. So we'll put that on the x-axis. Go ahead and plot that and spell geom histogram correctly this time. There we go. Okay, so clearly there's sort of a multimodal distribution here because we have these different species. So let's take a look at what the different species are looking like here with the fill argument in our ggplot call. Okay, and it looks like this Adelie species is sort of noticeably different from the other 2 here. It's a little bit hard to see, so I'm just going to go ahead and make these a little bit transparent. So that should just about do it, if I'm remembering correctly. Identity. Let's see. So if you do just alpha, it doesn't actually show through, which is a little bit annoying. So I'm just going to look up how to get the alpha values to actually allow multiple histograms to be seen. Plot parent, because I always forget how to do this. Overlaying histograms with ggplot2 in R. Position is identity. There we go. All right. Position equals identity. Spell that correctly. All right. So let's take a look at that. Cool. Okay. A little bit easier to see now. It's easier to see now that this chin strap species is actually sort of mostly occluded here. And you can tell there's sort of a lot fewer of them. We could go ahead and change this to sort of scale these appropriately. But instead, I'm just going to go ahead and take a look at some of our other values here to see what we're sort of messing around with. Okay, so bill depth is the next feature that I'm interested in. So I'll just go ahead and change that to depth, run that, and take a look. Okay, nice. So what I'm looking for here is are these features going to be useful in sort of a classification type task? It's looking like bill length is going to be really useful for sort of differentiating the Adeli species from these other two. And so that I'm hoping that bill depth will allow for some sort of differentiation between the two species that we couldn't differentiate between before, right? So the chin strap and the Gentoo species are pretty much on top of each other. So the bill length feature is not going to be too useful for telling apart these two species, but here we have some nice separation using the bill depth feature. So that's really useful. I'm going to go ahead and just create a scatter plot that will allow me to compare both of these two features at the same time. So I'm going to change fill to color. Histogram is going to become point. We don't need any of these parameters anymore. And then on the y-axis, I'm actually going to go ahead and put bill depth. Okay, and then this will instead be length. So let's go ahead and run that. Okay, cool. So as I suspected, right, it looks like we're able to sort of create three nice clusters that are pretty sort of easy to differentiate once you've taken into account both of these columns at the same time. So that's really promising for this data set. The iris data set doesn't have this feature as much. Two of the species are much more similar, and there's one species that's pretty different. Here it looks like the three species are sort of really different from each other once you take into account all of the different information. So it's really useful to know. What other columns am I sort of interested in looking at here? I guess we haven't taken a look at the flipper length column here, so I'll go ahead and take a look at that histogram as well, and I'll just stick this up here with our other histograms. All right, and we'll just go ahead and change that bill depth into flipper length, and then I think that's right. There we go. Okay, so let's go ahead and compare this with our other histograms here. It looks like this one also contains some unique variants that'll be useful in sort of classification. So that's also good to see. It looks like here the Gentoo species is sort of the outlier, the most different in terms of flipper length. So maybe it overlaps a little bit with the bill depth parameter, but who knows? Maybe some interactions there will still be useful for our model. Okay, and then I guess as long as we're making histograms, we'll go ahead and make more for body mass. So again, we'll just go ahead and change what variables on the x-axis here. You'll notice I am sort of getting these errors and warnings. The first one I'm not too worried about. That's just because I haven't set a value for bins. 2gplot is great at sort of picking a good value for me. But it does look like there's two values that are sort of consistently missing. And I'm noticing that across all of my histograms. So I'm actually just going to go ahead and fix that, because I think this is one of them. And I'm just going to quickly confirm that that is the case by typing view penguins, just to open it up in the view here. So here's the one that we saw in the head, and then scrolling down, there should be one more that's just all NAs somewhere. Okay, there's one more. Okay, and we shouldn't have any others. Great. So because it's only two that are missing, it's not really that interesting to be messing around with them. It's easier to just delete them. So I'll go ahead and say penguins is equal to penguins. I'll pipe that into filter, and I'll say not is NA, and we could just pick any of these columns here, and that should work. I'll go ahead and rerun all of my chunks, just so that the warnings that are here disappear. It's not going to change any of our histograms because I'm only throwing out two values. But there you go. Now those warnings are gone, and we got rid of those two penguins that we didn't have any interesting data on. Okay, so now that we've done that, we can go ahead and take a look at our body mass histogram. This one, again, it looks like there's sort of following a similar pattern here, that the Gentoo species is sort of noticeably different from the other two. The only place where this pattern isn't showing up is in bill length, so that's probably going to be a really important feature for us. Okay, cool. So that is all of the continuous information that we have. I'm not really too interested in this year column. I'm trying to do sort of a classification type analysis here. So I don't think year is going to be too useful for me. However, there might be something interesting sort of looking at sex, but specifically how these different variables change with sex. So this might not be too useful for our classification, but I am interested in finding out if I can use this data set as sort of an example of the usefulness of feature engineering, and sort of showing how manipulating factors can potentially be useful. So what I'm going to go ahead and do is just create a summarized data set here. I'll just call this penguins bill length by sex. And I'm just going to go ahead and look to see if there's sort of interesting differences across the two sexes in any of our variables here. So let's go ahead and group by our species. Oops. Species, there we go. Okay, and I'll go ahead and use summarize here. Also group by the sex column, there we go. There's some fancy new ways of doing sort of multiple operations at once using the across function in dplyr. I haven't taken the time to actually learn how to do that yet. So instead, I'm just going to copy these four names and just have some repetition in my code. Not ideal. At some point, I will learn how to use these cool functions. But at the moment, I do not know how to use them. So looking forward to learning a little bit more about those, because the summarize at and summarize if and summarize all columns that have been used to do some of these operations previously were, in my opinion, always kind of clunky. Okay, so let's look at bill length. And then we have flipper length. All right. Okay, and then last but not least, body mass G. Okay, so we'll just take the mean. We'll get the mean by species and by sex. Okay, so I'm going to go ahead and print this out. Let's see. Body mass G. There we go. Go ahead and print this out. I haven't actually gotten the difference yet. Okay, so there's still this NA. This NA is perhaps still here. Yeah, it's perhaps still here just because it's a level in the factor. I'm going to be a little bit lazy and just go ahead and filter it out here as well. Is A. Okay, I'm going to go ahead and just check. I see. So there is some missing sex information as well that I did not notice before. All right, so for this, let's go ahead and remove those missing values and take a look here. Okay, so this is what I was expecting. We've got these sorts of comparisons here. And what I'm interested in is just sort of comparing whether these differences are sort of particularly different across the species. Right, so I could go ahead and pivot this and sort of calculate the exact values, but I'm not really interested in the exact values. Instead, I'm just going to go ahead and plot it so that we can just sort of see visually what's going on here. Okay, so to do this, I'm going to create a bar plot. On my x-axis, I am going to go ahead and put the different species. And let's just start with bill depth to see if there's anything interesting happening here. And then our fill will be our sex column. Okay, and then a shortcut here is to use geomcall, which is just like geombar, except you don't have to put in the stat identity information. So now we can go ahead and run this and take a look. Although we do need position dodge, because we do not want stacked bar plots. Okay, so that will work. Okay, so for bill depth, it doesn't seem like there's a sort of a huge difference here. And I'm realizing now this variable name is pretty confusing, as I ended up doing all of the columns, so I'll change that variable name, go ahead and rerun that. It doesn't look like there's sort of any big differences here across the species. Maybe bill depth isn't the best one to look at. Let's go ahead and look at bill length. Not really interested in sort of keeping these plots around, so I'm just going to go ahead and use the same code and replace this information just to take a quick look. Again, no real sort of huge differences here. Taking a look at flipper length, again, nothing huge. Maybe there's sort of a bigger difference here compared to this species. Not too great. Body mass, this is sort of the one that I would expect to work if I was going to choose only one. And here it looks like there's maybe a little something here. It looks like here the Gentoo species has sort of a bigger difference in mass between males and females compared to especially the chin strap species. So that's good to know. It's interesting. It doesn't look like sex is going to be super informative in terms of a sort of classification type context, but it can't hurt to include. It'll help sort of contextualize some of these values. Maybe we'll include it as maybe an interaction with some of our continuous values that we're interested in. Okay, cool. So with that, that's pretty much what I wanted to do in terms of sort of exploring some of these values. I do want to sort of take a quick look and just see maybe there's sort of some interesting trends over the years. I'll go ahead and do that down here. I'm just going to create a really quick line plot. So similar to what we did here, although I'm going to be grouping by year instead of sex. And just to take a look, I'm not really interested in using any of that today. But just sort of for future projects, if I sort of want to use this data set more heavily, it would be nice to know if there's some sort of date type operations I could do with it. So, okay, we're going to do the same thing as before. Penguins is going to be piped into filter just to be safe. I didn't see if there was any missing year information, but there's no reason not to just sort of quickly add this line. I'll group by species and then year. Okay. Great. And then I'll summarize. For this, I think I will just grab the body mass. It's sort of the only thing I'm really interested in here. So in fact, I can go ahead and grab this whole line and just go ahead and copy paste that right there. Okay, cool. Go ahead and save my file real quick. Fix that spelling error. Okay, and now we have penguins by year. Go ahead and print this out. Take a look at it. Okay, so 3 years, 2007, 2008, 2009. Looks good. Just looking at the numbers, it doesn't seem like there's any super obvious trends, although maybe like 2008 was a particularly bad year for, or maybe a particularly good year for penguins. Hard to tell. Depends on the species. Well, go ahead and plot it and take a look, just in case it's a little bit more apparent, any patterns in the data. But I'm not optimistic that there's going to be sort of anything too interesting changing. Presumably, all of these penguins live for a lot longer than 3 years, so I wouldn't imagine there's a ton of change happening year by year. But go ahead and take a look before concluding that. On our x-axis, we'll put year, we'll put body mass in grams on our y-axis, and then we'll just go ahead and put the color as the species. Okay, and then to make this easy to look at, we'll go ahead and make a line plot, and then we'll just add a geom point as well. Go ahead and look at this. Hopefully our lines look okay. Yeah, okay. Nothing too interesting here, really. It's treating years as a integer value, so that's probably something to go ahead and fix, but already you can tell nothing sort of really interesting happening year by year. So good to know that if I was going to do some sort of trends over time, some time series stuff, this is maybe not the data set for that. To be fair, the iris data set doesn't really have any of that either, so can't criticize this package too much for it. Okay, so let's go ahead and make some models. Let's start with just sort of like a simple linear regression here to get started. I think the most interesting thing to predict will be the body mass. That seems sort of the most interesting one to me. So let's go ahead and just build a quick linear model, and we'll see how this goes. We'll go ahead and use the LM function to do that. Data is penguins. All right, and I'll just go ahead and put that on its own line. Body mass G is the thing we're predicting. And let's see, I want to make sure, because I think I'm probably going to use that sex column, I'm going to go ahead and say we don't want any missing sex information as well. So go ahead and run that. And just to check, I want to see if there's sort of any missing information here. Penguins. Let's go ahead and pipe this into group by. Or better yet, we can just pick one of these columns and take a look quickly. So let's take a look at penguins. Let's try body mass, because we want to make sure none of that is missing. Okay, and then that's going to be interpreted as a Boolean. So we can just use mean on it and just see. Okay, none of that is missing. Great. So scrolling back down here to where we're constructing our linear model. Body mass is going to be predicted by, let's start with species, because we know that's going to be sort of particularly important. And then these other variables, bill length and flipper length, probably are also going to have some useful value to our model. Sex we know is going to be sort of particularly important. So let's go ahead and include the interaction with sex. And we'll just go ahead and work from here. This will be sort of like a baseline just to see how we're doing. Put a comma here. And we'll just output the summary of that model. All right, so let's take a look at this here. First thing I want to see is our model even any good? Somewhat unsurprisingly, this is like some pretty useful information. Our model is doing okay. So an R squared of 0.85, adjusted R squared is going to be basically the same because we're only including 3 parameters here. That's pretty good. Pretty good for only these 3 parameters. And it looks like basically all of our columns here are useful, which is nice. It's also nice to see, I mentioned that these values were already going to be treated as factors. Sex is a factor and species is a factor. This is not true in the iris dataset, which is a huge pain. So I'm really happy that that's the case here. I can just sort of throw this into a model without having to worry about converting any of that stuff. I get all of my properly coded interactions, so that's great. Okay, so that's sort of our baseline. Let's see if we can do a little bit better just by adding in some of this additional information here. We can go ahead and add our bill length and our bill depth. So just for convenience here, I'm going to plot out all the column names or print out all the column names so I can just copy paste here. Okay, so I definitely want bill length and depth and flipper. There's a bit of a question about whether a species should interact with all of these and sex should interact with all of these. The answer is probably yes, although we sort of have a limited number of rows here, 333, so I don't want to add too many parameters here, just out of sort of totally overfitting. So let's go ahead and start here without these interactions and take a look. Bill length, bill depth, and flipper length all seem to be useful, at least they're all significant. so that's good to know. We can take a look at our adjusted R-squared. 0.88, okay, a little bit better. Nothing crazy. It makes sense. Species and sex are probably going to be by far the most important thing for predicting body mass. I wonder, do we have a plot of those two variables? We don't. So I'm going to go ahead and just plot out sort of the relationship that we're picking up on here with just species and sex. Because it looks like that sort of captured most of the variance in our data, and so I just want to take a look at what that looks like. So I'm going to go ahead and create a scatter plot. Let's see. I guess we do have this. We do have this in a bar plot, don't we? Species and sex and body mass. Yeah. Yeah. So we do have that there. I do want to sort of take a look at what that looks like. But maybe instead of creating a plot here, maybe instead what I'm interested in is just taking a peek at these residuals. So a scatter plot is not going to be too informative because we only have the single continuous value. Let's go ahead and just take a look at the residuals here, just to see if there's sort of anything interesting, any interesting patterns there that we could potentially take advantage of. Okay, we can go ahead and plot. I think we can just call plot directly on the residuals, and that'll be somewhat interesting. Okay, so doing this is just showing us the residuals by index, right, which is not sort of ordered by anything interesting, but it is useful for sort of taking a look at general trends. We have to be a little bit careful because there is some order to our data set, right? Like all of the first species are going to be all of these. In general, our residuals look sort of nicely normally distributed, so that's nice. No sort of obvious patterns are sticking out here. It looks like we're sort of within 500 grams, which makes sense, right? Sort of the scale we're working with here is, you know, somewhere around 3,000 grams. So cool. I mean, that's pretty good. It's nice that there's a pretty easy linear model that we can sort of directly pull out of the data with just a couple of parameters and get sort of a nice R-squared value. So happy to see that. Let's see. I think the last thing I want to do here before I go ahead and call it for today is just doing a logistic regression. And I noticed there were sort of these two species that were the most similar in our histograms. I think it was this Adeli and Chinstrap were sort of consistently on top of each other. So let's go ahead and see if we can just differentiate between those two. It's a little bit sort of simpler than doing a logistic regression. With 3 categories, I'll just make our problem a little bit easier here. Just to get a sense of if this is the sort of thing that is going to be fairly straightforward to do. You can get like a decent R value, at least as far as a simple sort of intro data set goes. Okay, so just checking that Gentoo is in fact the one we want to get rid of. Yep. I'll go ahead and use filter just to remove those from our data set for now. So species is not equal to Gentoo. Okay, and that should be in quotes. There we go. Okay. Go ahead and run that. And I'm looking for it in my environment. The species names are probably capitalized, which is why none of those got removed. Go ahead and run that again. Okay, 214 penguins left over. Great. Go ahead and scroll back down. Sorry about that. Okay, so we just have this Adelie species and this chinstrap species. So let's go ahead and try to differentiate between them. I'm actually not sure if the built-in GLM function can handle these in factor form. So we'll go ahead and try, leave them as is, and just see how it goes. I'm not going to include the island because this one species only shows up on this one island, so that sort of trivializes the problem a little bit. Instead, I'm just going to start with, let's go ahead and say body mass and sex and see sort of how far we get with that as kind of a baseline. And then we'll see about adding in some of these additional factors. Okay, so to do a logistic regression, we'll use GLM instead of LM. And I like to just sort of fill in these arguments first so that I don't forget. Data is our newly filtered data set, and then our family is going to be, oops, go ahead and make sure I get this string right here. Go ahead and scroll down to the examples. Make this a little bit bigger, just so that I have some room to play with and look at this. Okay, not gamma. Okay, not particularly useful. I forget if it is binomial. I believe it is, but let me just double check here. Our logistic regression GLM. Okay, family binomial. There we go. Okay, and then our link is going to be logit. Okay, cool. So let me go ahead and stick that on a new line. And same as before, we will go ahead and try to predict species this time. So, like I said, I'm not sure if this is going to work because it's a factor, but we'll go ahead and see. And we'll just go sex, and this time body mass G. Okay, so go ahead and call that logistic fit. Tab this over, make that look a little bit nicer. Logistic fit. All right, let's go ahead and run that. Unused argument link. Okay, I think that goes in the family call, but it should be logit by default. As you can see, I don't run my logistic regressions as a frequentist analysis very often, so bear with me as I remember the syntax to use GLM. Okay, so that worked nicely. So it did work, even though it's a factor. That's good to see. And now let's go ahead and take a look. The estimates are a little bit harder to interpret. These are going to be in log odds, but that's fine. We can still look at our null and residual deviance and just sort of get a sense of how we're doing here. Okay, seems like we are doing pretty well. I want to go ahead and just get an accuracy score from this fit. So I will go ahead and use predict to do that. Predict. We want to call that on our fit. And then, let's see, I think by default it might have access to the data. It does. And there should be 214 values, and there are. So preds is going to be equal to predict. And then I'm just going to take this, and we will just add this to the end of this data frame. So let's call this with predictions, and then we can go ahead and just cbind this column on. Okay, go ahead and run that. Take a look, make sure that looks right. Okay, so here's our prediction. Cool. Okay, so interestingly, I'm seeing what looks to be like not actual predictions, but the sort of log output. So let me just pull up the predict GLM docs, and I will go ahead and check that we have the correct arguments here to actually get it in the form of zeros and ones. Predicted probabilities. Okay, so let's go ahead and do type equals response here. It's a little bit more interpretable. Run that, pull this up again. Okay, there we go. So now we are getting a value between 0 and 1, where 1 is going to be chin strap. Okay, and it looks like all of our predictions are going to be less than 0.05, except perhaps in the rare case. I think I saw 1. I'll go ahead and sort this so we can take a look. Yeah, so there's just a couple of these where they look like they are clearly chin straps. This is because there's going to be some balance issues in our data set. We already sort of paid attention to that before. We saw that chin straps were a little bit less common than the Adelie species. And so most of our predictions are probably going to be weighted, right? Unless we have some sort of particularly strong evidence. So the takeaway from that is, right, our model is not going to be really great at differentiating. We never sort of really have enough information to be really sure that we're dealing with a chin strap penguin, and so we are sort of weighted heavily towards the default of this Adelie. We can take a look though and see we should be seeing sort of more chin straps towards the top. And it looks like that's the case. But let's go ahead and just check how we do if we add some more information to our model here. So we can go ahead and compare our output to this model here. So let's go ahead and pull that summary information back up. We have this AIC value. We can see here, right, our deviance barely decreased at all, so it makes sense that our model is not really performing particularly well, even though all our values are significant. Maybe adding a few more things in here will sort of help that out. So let me scroll up to get my column names to actually remember what the names of the columns are. Go ahead and look at bill length, bill depth, and flipper length, Okay, Okay, we'll call this just logistic fit 2. Fix the spacing. Go ahead and run this. Okay, and it looks like there is probably some collinearity here that we're dealing with, because suddenly all of our values are not significant. We can take a look at this here to see if our model is actually performing better. And it looks like our model is performing way better. So let's go ahead and take a look at these predictions. So even though we lost the significance in the sort of individual coefficients, we should probably look to see maybe like bill length and bill depth are sort of giving us the same information. Even though that's the case, our model as a whole is performing way better. AIC is something we want to minimize. So the fact that it went from 265 to 14 shows that our model has gotten a lot better. So that's good. Go ahead and check out these predictions here to see if that is sort of consistent. I'll call this preds 2 just so that we don't overwrite anything. I guess we'll call that preds 2 as well. Okay. So let's take a look here. This is our second one. Pull that up. Okay. This is an incredibly small value, which means it's getting sort of a very strong prediction. And hopefully when we sort the other way, we'll see values very close to 1. And we do. Okay, so just like that, it looks like we included enough information in our model such that pretty much all of these predictions are extremely confident. Now, whether our model is sort of actually performing well, hard to tell, right? We are testing it on the exact same data that we're training it on. We could be just like super overfit. But it does look like there's sort of a lot of information here that we can use for this sort of classification task, which is great. I'm really happy. I'm glad I got a chance to sort of play around with this data set and have some fun with it. It has some really nice properties. I hope any of you out there who are watching this maybe picked up a trick or two or learned a little bit about this data set as well. If you liked what you saw, I hope you'll stick around and maybe come back to one of our true live streams in the future, now that I've gotten a little bit more experience and a little bit more practice. And yeah, I hope you learn something new and have some fun. All right, so I think that's going to do it for me today. If you did have fun, and maybe there's a topic for a tutorial that you want to see, in my YouTube description there is a form that you can go ahead and fill out some topics that maybe you're interested in, and I can pick those up for a future week. So, all right, that's it for me. I'm going to go ahead and sign off, and I'll see you next time.